cell. Sorry. So the cells that we are interested in are basically marine microalgae, and despite that they are micrometer size only, they are very important primary producers. Basically, they are responsible for almost half of primary production. They drive essential biogeochemical processes, and happens to them basically will influence on the higher trophic level. Those cells, they are unicellular marine algae. They have pronounced motility, which enables to form a stable suspension, so they don't aggregate. And one of their feature is that they are known as a naked cell, which means that they possess only a thin elastic plasma membrane covered with a mucous surface coat. So in our group, we have a long tradition to study interfacial behavior of a different system, basically soft system, such as organic droplets, lipid vesicles, or cells. And referring to the previous plenary talk of Massimo, when he showed behavior of stem cell at a modified surface and how that spreading looks like. Over here, I'm showing the different aspect. This is that how the macroscopic droplets will fill the substrate if we change the applied potential on the substrate only. So we don't have a chemical modification here, we are just applying different potential or different surface charge density at the interface. So this is the photography of macroscopic hydrocarbon droplets. So we have hydrophobic droplet that is deposited to the charged interface, and depending on the energy of the surface, the macroscopic droplet will form different shapes. So if the energy of the surface is favorable, then we have a maximum adhesion, which over here it's the droplet forms the lens. When we shift potential to more negative, then from this lens the droplet contract and it forms a semisphere, and by further shifting potential more negative, this contact area more decreases and it forms more spherical shape with a very small contact area, and at the end this droplet detach and by buoyancy go to the surface. So this just shows a manifestation of how with the potential we can fine-tune the adhesion forces. Of course, it's very much important that surface properties of the three interfaces in contact. So over here we have the surface properties of the hydrocarbon with our substrate, and hydrocarbon with the water, and water with the substrate. So all these surface properties basically influence whether this process will go spontaneous and how fast it will go. Due to this feature that these hydrocarbon droplets are very soft and deformable, and we are dealing with the cells that are as well soft, naked, therefore deformable, we are interested to find surface properties of the cell as a more complex system. Therefore, the aim of our study was to examine nanomechanical properties of the cell and as well adhesion dynamics of algal cell in two phases of growth. That means when cells are in exponential and in stationary phase, using complementary surface methods and mathematical modeling. So here is the basic principle of our approach. Over here, it's giving how this electrochemical adhesion-based detection works. Electrochemical adhesion-based detection is based on the feeling interfacial properties, hydrophobicity and structural organization, rather than the chemical composition. And basically, when we have a soft particle in our aqueous electrolyte solution, we have our charged electrode system. By stochastically, when a particle collide with the electrode, makes attachment, it sweeps this charge from the interface, and then this deformable particle just deform and spread over the interface, forming the film, which is monomolecular thickness. So this charge displacement, due to this contact and spreading, we can register as a well-defined amperometric signal. So basically the signal is evidence that this interaction of the particle with the electrode happens. So the information that we get from electrochemical adhesion-based detection is this amperometric signal, which then gives us information about thermodynamics and the kinetics of the adhesion process. On the other side, atomic force microscopy enable us to give the information about the high resolution imaging and as well mechanical properties on the nanometric scale, and as well over here we have manifestation of the interaction forces between the probe and cells. What is as well important to stress out is that whether this interaction of the particle with the electrode will go spontaneous or no, it's defined thermodynamically with this Young-Dupré equation. So that means that it's not that any collision of the particle will lead to the film. So now we start to determine these nanomechanical properties of a cell. We face the challenge to work with those algae because they have pronounced motility. They swim very fast. So due to that, we have to develop adaptive protocol for their immobilization on the substrate. And we did it on such a way that after the glass slide was cleaned well and treated in plasma, we put the polyethylene polymer at the glass, which makes the surface positively charged and makes electrostatic binding with a negatively charged cell. So interesting and very exciting situation happened when the cell became attached, but the fact that the flagella of the cell still keep moving, giving us information that we are dealing with a live cell. So over here it's presented the height images of the cell in exponential and in stationary phase. And as well, it shows this profile of a cell in exponential phase is quite larger than for the cells in stationary phase. But what is important to note is that due to this dimension and height give us information that we had only attached cell to the substrate. They didn't break, neither leak. So the main dimension of the cell, 9 by 6 by 6 micrometer, was kept. By analysis, it was an analysis, and we found that the volume of the cell in exponential phase is statistically larger, and in contrast to the cells in stationary phase, and which is probably due to the prior to the cell division. Regarding roughness, so we haven't found any difference in surface roughness of the cell between the cell in exponential and stationary phase. Next, we determined elasticity of those cells. Over here again we have a cell in exponential and stationary phase at a designated cell surface area. Over here it's produced elasticity maps expressed in Young's modulus. And it was found that the cell in exponential phase are stiffer, which is statistically, again, a significant difference in contrast to the cell in stationary phase. It's interesting to say that those algal cell, naked species that possess only the plasma membrane, has this Young's modulus in the orders of magnitude of kilopascal, while, for example, for the cells that possess cell wall, silica cell wall, that Young's modulus is 3 orders of magnitude higher, that is like in a megapascal. And why I'm saying that is if we know their elasticity or how they are stiff, that give us information whether those cells in environment system will be fragile or more vulnerable during some perturbance. Further, we were interested as well to examine the hydrophobicity of the cell in 2 phases of growth. So over here again we have topographic images of cell in exponential and stationary phase. At the designated area is shown this adhesion force maps. And we measure those hydrophobicity by modifying cantilever with dodecantiol. So we have then a hydrophobic probe. And this adhesion force map show us pronounced difference between cell in exponential versus cell in stationary phase. And this difference in adhesion force as well show a statistically significant difference. Basically, it takes a larger adhesion force necessary in interaction between the hydrophobically modified tip and the cell in exponential phase, which means basically that cell in exponential phase is more hydrophobic. So this difference in cell hydrophobicity basically shows that there is molecular modification of the cell envelope during this aging process. So now, since we determine these main nanomechanical properties of the cell, now we will go further to examine the process. Because the nanomechanical properties of the cell, they determine the adhesion process. So over here it's shown the basic mechanism of the cell adhesion at the charged interface. So again, we have cell that freely swim in the interface. Over here it's our charged interface. The current is 0 because there's no attachment. When cell come to the interface, it displays this surface charge. It displays this surface charge. It forms the micropores at the cell membrane. It deforms and flattens, and this is shown as an increase in a displacement current. And then a cell further flatten and it break. We have a macropores at the cell membrane, and as well this intracellular material further released over the interface and displays more charge, which we register as a descending part of this signal. So this is the amperometric signal of the single cell. So each signal corresponds to the single cell interaction with the interface. And since the signals are pretty similar in the shape and in duration, we can really say that we have monodispersed system. well defined. So those signals last just 4 milliseconds, or from 4 to 6, so they are very fast transients. And this fast adhesion and spreading process is as well stimulated by the type of substrate, because we are working on the fluid substrate. Our substrate is the mercury interface. So the advantage of such a substrate, besides the fluidity, which basically perfectly mimics the interaction with the other fluid interface in contacts, is that such a substrate is conductive and electrified. And as well, we can change adhesion energy and the surface charge density, electrical field strengths, just by changing applied potential. What is interesting is that when we change the polarity of our applied potential, surface charge density, from positive going to the negative, then we obtain the reverse mirror images, which is proof really that the double layer, that our signal originate from the double layer charge displacement. The information that we can get from those signals is that we can integrate the area beneath the signal and calculate how much surface charge become displaced by the cell, and this charge is proportional to the cell size. And further, by taking into the ratio that displaced charge with the surface charge density of the electrode, we can calculate the contact area that cells forms at the interface. So now we have those amperometric signal of cells. So let's see how those amperometric signals looks when we have a cell into phase of growth. So here is the signal shape of cell in exponential and in stationary phase. It's obvious that there is a difference in the signal shape, but as well a signal duration. Over here, the signal duration is much more longer, and of course, the displaced charge is much more larger. So now we have signals, and we wanna know what is the kinetics of the adhesion process. So since the signal are pretty fast transients, as I said, 4 milliseconds, the only way to do it is to employ mathematical modeling. To do this, we developed the reaction kinetic model of the three-step process, where this interaction of the cell with the electrode includes 4 states. So we say, okay, let's see, this is the intact state of the cell, this is the formed cell, this is ruptured cell, and this is a final state. So basically this final state is what it describes our signal. These states are connected with a forward and backwards rate constant, and each state change in time. And we got as well the analytical solution of this each individual state, but I'm not going to in detail here. And this final state is expressed in electrical equivalent in order to be used for amperometric measurements. So this D, which is final state of information, we transfer to current in order to be used for the fitting our amperometric signal. And more information about the model are shown in this reference here. So just to give you an example how it works. So this is our amperometric signal of cell that contain primary and secondary part. This primary part of the signal could be fitted with the model very well. The experimental data are shown with an open circle, and the fit is shown with a solid line. From the primary part of the signal, we were able to extract time constants of the process that associate with the attachment, deformation, and spreading. And from secondary part of the signal, it's fitted with empirically with the 2 exponential functions of time, from which we obtain another 2 time constants of the process. So when we know this time individual time constants, then we are able to go back to our analytical solution for each individual state and follow what happened with change of individual state in time. So then we can say that at the beginning of our signal, it's present only intact state, all other state are 0. At the half of the current amplitude, predominant state is state B, while the state D of film, it's present just 3%. At the time of current amplitude, predominant state is ruptured state. At that time, intact state is equal to 0. And at this point, the film is as well very predominant. So basically, the model enables us to decouple these individual states and follow them in time, and then reversibly to get information about the cell transformation at the electrode. From this secondary part of signal, besides getting these time constants of the process that are rate limiting step, we can as well obtain information overall from this contact interface area. And by taking into the account the volume of the cell from atomic force measurements, we were able to calculate the film thickness in time. So we have this graph shows how the contact area of the cell at the interface increase, and at the same time how the thickness of the film decrease until it comes to the 5 nanometer thickness at the end, which is at the end of the signal. Sorry. So here is our amperometric signal of cell in in exponential phase and stationary phase that I already described. So again, experimental data and black solid line, it's a fit, which is very good. So more about this, as I said, it's written about the method and methodology developed. It's written in these references here. And what is visible from the first glance, that this surface area beneath the signal of the cell in exponential phase is much more larger, which basically means that we have larger cell, which is as well in agreement with the atomic force measurements, where it was found that cell in exponential phase is larger. Okay, so in this table it summarizes this determined time constants of the adhesion process. For the cell in exponential and stationary phase, over here we have time constant associated with attachment, deformation, spreading, and this slowest time constant from the secondary part of the signal. And what is visible, that cell in stationary phase much more faster adhere and spread over the interface. So this difference in time constant for the adhesion and spreading basically show us, basically reflects the surface properties of the cell. So we said that the cell in exponential phase are more stiffer, more hydrophobic, and have a larger volume. So that is all reflect on the adhesion dynamics. Just for the comparison, let's say for the cell, this time adhesion time constant that determines the whole process is 1 millisecond. But for example, if we have a lipid vesicle, where for the adhesion we have only membrane and inside it's aqueous electrolyte solution, that process is 10 times faster because there's no intracellular content. And further, regarding thermodynamics, over here in the table is shown critical interfacial tension for cell adhesion. It's basically this parameter give us information what energy of the surface is necessary. It's minimal energy necessary that the adhesion happens. So when we add a negatively charged electrode, this difference is about 30 millijoule per square meter. So which means that really there is pronounced difference in the energy necessary for the adhesion and for their rupture and spreading, meaning that cell in exponential phase is really harder to break than for cell in a stationary phase. As well, those results are in analogy with the behavior of hydrocarbon droplets at the interface. I mean hydrocarbon droplets of different polarity. So by increasing polarity, the interfacial tension decreases. So that's as well a good comparison. So here is the conclusion. So we show that nanomechanical properties of the algal cell depends on their physiological state. Age-related loss of cell elasticity and hydrophobicity could be attributed to the molecular modification of the cell envelope, which then consequently reflects on the cell adhesion dynamics at the interface. Cell mechanical properties maybe in the future could be considered as a marker for environmental stress in order to understand better viability and adaptation strategy of algae during their growth in aquatic system. I would like to thank the collaborator who was involved in this study. This is a group from Institute of Pharmacology and Structural Biology from Toulouse. They did the atomic force measurements, Flavien Pilet, Etienne Dag, and Marie-Pierre Rolls, and as well my colleagues from the Institute Ruđer Bošković, Jadranka Pečar-Ilić, and Professor Ružić, who was in charge to develop the mathematical model and corresponding methodology for amperometric signal analysis. And I would just like to invite you once again for this International School of Biophysics that is meant for the PhD students and postdocs. It will be in Split this summer, a very nice location. We will have hands-on workshops going on with molecular dynamic simulation, mass spectrometry, atomic force microscopy. And the deadline is already over for applying for the grants. But according to the chair note, he's willing to extend the deadline for the members of this regional biophysical congress for another week or so. So if you're interested, please take this opportunity. Thank you for your attention.
Thank you. So the paper is now open for discussions. Are there any questions?
So you said when you're showing these AFM measurements that you can see that these flagellas are still moving.
Yes.
But this is inspected before the AFM measurements, or?
Yes, because you have such a setup which is inverted optical microscope and AFM above. So basically, when you come to the right place, then you see if the cell is immobilized, and really. This fact that we have a flagella that was basically a problem, we use as advantage to just to examine that they are still alive. So it was a good feature at the end.
So just a curiosity, do you know the orientation the cells are, doing this addition? So I mean that it's a random orientation. So do the signal change depending on the orientation, or can you control the orientation? Because in the picture you just show that the flagella are at the top, but they can also go at the bottom.
So we cannot control any orientation, neither because it's a stochastic event. We don't have any active or inner channeling or anything. So it's stochastic. We cannot say anything about the orientation for the cell. But what we did is for the simple system, and that was recently published before like a year, but for the lipid vesicles and for the hydrocarbon molecules. So for that, we combine the electrochemical approach with the molecular dynamic simulation, where in molecular dynamic simulation was developed like this electrode interface area with a different potential at the electrode. We put the molecules, and then we look the orientation of the polar head groups vice the tails, to see how this orientation change with the applied potential. And then we can say for such a simple system whether it's head or tail preferences, affinity, and binding kinetics, etc. So for the simple system we can say, but for the cell we cannot. Thank you.
Okay, if there are no further questions, then we thank Dr. Ivo. And then I would like to invite our